Okay, so I'm resuming the earlier video and we're going to continue with our example. So anyhow, how does that work? So the actual screen itself, this whole little project, Grid Play, sets up to build both of the grids, and he's got all of our row calculations and all of our point calculations in here for the two different grid styles. Um, at some point, I'm probably going to go ahead and add square in here as well. But it's got all the lerp points and all these other functional calculations in here for calculating distance and the uh, point 0 to point 1 and then returning the list of points. This this is the guy that does the work in getting from point A to point B, okay? And so what I'm doing is an arbitrary division of this distance based on dividing by 40, which is, it's, not the best, not the worst. It works pretty good. It gets about 95%, way over, in my opinion. The other point of nudging that you get is the fudge factor of these points that we're using. I am not really using the center of the source hex to the center of the destination hex. Okay. So when let's come over, let's see, this is building the grids themselves. We don't really care about that. Okay. So when we come down here, and you left click the grid, that sets our starting point, okay? So we have our starting point here, and it's kept at, we load it all into the map. This is the button build, sorry. This is where we're left clicking the button build to do all that work. Okay, here's the canvas grid. And so we select the hex just like we do in the game and every place else I've done it. And then we go ahead and we get our cursor point. Cursor point is the math being calculated. As you move the cursor around, he's actually tracking what that is in something called a cursor point structure. He's tracking the X and Y, and then he does the calculation to turn cursor point to where he has the row and column based on where your cursor is in the actual hex. Okay, so down here, we carry that a step farther. So originally, you clicked some point on the screen. Let's say you're going for hex 00, right? And you clicked, maybe it's pixel 5 and pixel 9, vertical and horizontal. Okay. That's what's being tracked in cursor point in the XY at the top of this when he's actually tracking your cursor. Now, what happens up there is he takes that X and Y and looks up the row and column on cursor point. So now I know that that's row and column are 0 and 0. So down here, I turn that around and say, okay, I know I got the row and column of 0, 0. Get me the X and Y of that cell. So this is going to return the top left corner as X and Y in the calculation. Okay, so if I was going to paste a 64 by 64 PNG graphic into that cell, that's the coordinates where I would paste that in. Okay, so we have the cursor point. I go ahead and calculate and grab the hex. So this is our source hex. And now, real easily, we go in and say, when you right click the grid, then what he does is the exact same thing. And he calculates the the destination based on your right click, and then he calls this new pathing and passes in a reference handle to the map that we have on the screen, and he's got his information of what his rows and columns and what kind of grid you have, and then he gets his source and destination hex. Okay, so I'm going to control double click that to jump to this function so we can start the math off. So what we're going to do in here is convert from row and hex to point P0 and P1, or you could call them 1 and 2, from and to, whatever you want to call them. But these are point structures. All a point structure is X and Y. You don't actually create it. It just exists. I think it's a Microsoft that we actually have access to in their world. Okay. So don't look for a structure called point in my code because it doesn't exist. That's a freebie by PureBasic of the shell of Microsoft here. So we create a list of points as well called path. And then we get we create a map point called center. And the goal is to get the center of both of those cells. Now, here's where our nudge comes in. We get the X and Y, and normally you would think we would, since our grid is 64, we would add 32 to X and Y to get to 0, and then, or the center, and do that at both ends. Well, what I've chosen to do is he's actually going to draw the line from plus 30 to 38, and we could probably even skew this to 28 if you wanted. All right. So this is the nudge calculation that we do. So it's not center to center. If you come up here and look at the grid, if you calculated a line center to center, then we're in deep trouble. And that's one of the problems I kept having. If I went from that hex to this hex, he would draw a straight line. But we don't want him to draw a straight line. So what we've done is modified the beginning and end point to be a little bit off center. That way our line crosses, we actually add to it. So he's going from 28 on the source, so that's a little higher, and then he's going to 38 on the destination off center. So he's drawing a line that's not straight between these two hexes, which causes it to dip into this lower hex. And therefore, when he's doing the calculation along the length of that line, he can identify that, oh, hey, I break this up into pieces every 40 pixels. I break that straight line up into 40 pixel pieces, really. And then he, at the 40 point, he looks at it and goes, hey, what grid are you in? And then he goes, oh, well, you're in this one down here, and then the destination is in the one up there. So then all of a sudden I have 3 points. You see how that works? So even if you make the line longer, then you actually have, when it gets really close and you got a bigger distance you're going, whether that line traverses a little above or a little below doesn't really matter, just so that it really does make a little bit of difference. And again, this 28 and 38, maybe it would be better. Why don't we say, let's make them 28 and 28, huh? That way they're both skewed the same direction. And I guess that would be a little bit more symmetrical to the eyes, where we always go up or we always go down on that calculation. So let's see. We'll come in here and select him, come across, and of course he goes up, and we come across, and then he always goes up. Do you see that? He's going up, because this line is now written above that line, above that center line. It's not really drawn through that. Okay, he draws a straight line from source to destination a little higher than center, and then tracks it every 40 pixels and says, hey, what cell are you in? What cell are you in? What cell are you in? And then we gather up those cells, and then that's what I then turn back into row and column and calculate their centers and then draw the line there. Okay, that is how this whole thing works. Now, you have a bit of difference here, because if I draw a vertical grid and we go sideways, it's just a straight line. So the math between these two types of grids is also the biggest determining factor, is how do you go from this cell here that's now cubed in red and go northeast, northwest, or northwest, northeast, east, west, southwest, or southeast. What do I have to do to this coordinate, axial coordinates, to get to this cell? Well, he's going up a row, so -1 row, but that's 0 and this is 0. So our column didn't change. So that's a -1, 0, -1 to row and a +0 to column. Okay. If I was going from here up to this cell, well, let's see, that's 0, 1. This is 1, 0. So that's going to be a -1 on the row and a +1 on the column. Okay. Now, if I change it around, because this is the, let's see, 0, 1, this is the odd row. If I look at this cell, for instance, then my math is completely different to get to his surrounding cells. To go northeast is actually backing up a column and it's backing up a row. So that's a -1, -1. Okay? See how that math goes as you traverse moving from that cell. Now, the formulas take this all into play. Okay? So if we come over to the axial grid math sheet, at the top, the one kind of kludgy thing I did was I double dipped the use of north and south. So I wanted my directions to be 6, okay? And so when we spin the center hex, regardless of grid, there are 6 directions to go always. So I did the math such that north is north when it's on one grid and north is east on the other grid. Okay, so on the pointy tops, it's east, and on the flat tops, it's north. But it doesn't matter because all it is a value of 0 to 5. Okay, now we have parity, and that's whether your column or row, depending on your grid, is even or odd. And yeah, there's 2 of them, so you get 2 sets. Now, we have one directional difference procedure, and he takes grid type as a parameter. Okay, he takes parity, direction, and he's going to load up this vector object based on grid type. Now, it's important to know before you get to that lowest level, you're actually calling a get me a neighbor hex, and this is a pointy hex versus a flat hex. So at the time these functions are called, I need to know what grid I'm playing with, all right? Because I need to know whether we're calculating a grid offset, a row being even, or are we playing that a column is even or odd? Okay, so these guys all kind of stack together. And so the real entry point is calling get the hex neighbor. And then that all rolls up into this guy. Now, this is where the real work is done, to be honest with you. This is a pain in the butt because you come in and you got your grid type of grid hex horizontal. So that tells me that we're dealing with the flat top grids. And so here's my directional vector. If I'm going southeast, that's a +1 row, +1 column. And this is where all that math comes in. So if its parity is even, it's this set. If the parity is odd, it's this set of numbers. If you're dealing with a vertical grid, then the even is rows, not columns, and the directional differences, vector elements, are here. And though I'm using north, it's really west, and I'm using south, but it's really west. Okay, and then down here you have the east and west as well. Okay, or east and west. South is east. Sorry, I comments wrong. East, right? Okay, so that is where this math is hidden. I don't really mean to say hidden, but that it kind of is pretty buried under all of this. When you come down here and call the functions like reachable hex, this has to actually be called if we're playing a grid maneuver like we are or he is here, okay? Because he can't walk through these light blue cells. He can only walk where it's black, okay? So he's put all this crap in the way, so he has to find his path. So that I haven't built that into this yet. I don't have a smooth way to get that in there. Eventually, I probably will. I'm not sure to be completely honest. I'm not sure, but I have a task in my head that says do it. So that's where the reachable hex comes in. Can you get there? And so what we're going to have to do is come back with a list of reachable hexes. And these are the only hexes that you can use when you're actually doing that draw the line and distance piece, is the marriage of this to the marriage of this other chunk of code over here. Now, that's how this works. And I know it's to quote a movie character, that's about as clear as peanut butter, good old Yukon Cornelius. And it is a complex animal. There's nothing easy or straightforward about doing this. There's a certain amount of elegance in the code. And to be honest with you, I think it's just downright amazing how fast it is and the how this is all working and playing out. So yeah, that pretty much is this video. Um, I would love to hear some comments if y'all got some comments, but I'll eventually get this out onto the web for y'all to play with and take apart and study and figure out how it works and why. And maybe I will take on the task of throwing in random blocked hexes that we have to go around and try to do some pathing or something in here. Not quite sure how that would materialize at the moment, but we'll see. I want to thank y'all very much for watching, and we'll get together again soon on the next video.